Now, the first theorem of linear transformation of today's class is given as follows. It is called, it is saying that let V and W, okay, be vector spaces, and let T colon V to W be linear. Then T is 1 to 1. T is 1 to 1 if and only if NT, null space of T, contains only singleton zero. That is the zero vector of the vector space. Okay, so that is a very important theorem, very, very important theorem. So you have to keep this in mind. Now, this theorem, according to the book, it is theorem number 2.4. Proof is there given in the book, so I'm not going to discuss it. The proof is very simple. And the second theorem which I want to write over here, it is theorem 2.5. And it is saying that let capital V and W be vector spaces, okay, of equal finite dimension, and let T colon V to W be linear, then the following statements are equivalent. The following statements are equivalent. So number one is T is 1 to 1. T is 1 to 1. Number two is T is onto. Number three is rank of T is equal to dimension V. Rank of T is equal to dimension V. Now this result is actually very important, and very, very important from many points of view. From examples, if you want to solve the examples, then it helps you a lot. If you talk about the competitive examination, this particular example actually is very important, because a question you are going to get from the competitive examination, from this particular section. Then if you talk about can you hear me? Just say yes or no. Can you hear me? Because I'm not able to. Okay. So from competitive examinations point of view, it is very important. And if you are actually talking about the other engineering topics which I talked last time, like deep learning, neural network, and quantum computing, this particular result is also very important. These results, the entire book of Friedberg is actually very important. And if you can finish the book till the end, even if it is not there in the syllabus, so that will be beneficial for you. The rest is up to you. I'm not pressurizing anyone. For your reminder, it is you rank T as discussed in the last class. It was dimension of range of T, range space of T. That was rank T. Okay. And probably you can remember the theorem that, and you see NT is sometimes called the kernel of T, and dimension of NT or kernel T, it is called nullity of T. And there is a very important theorem which says that nullity of T plus rank of T is equal to dimension of the vector space V. Okay, and this sometimes according to your syllabus, this theorem is also called rank nullity theorem. You can find it in your syllabus, rank nullity theorem. Okay, so these things are very helpful in solving problems. So I am going to solve a problem for you first of all, and then I'm going to ask you to solve a problem by yourself. Okay, so let us start with the problem. So the problem I'm talking about is given in exercise. In exercise, it is problem number 2. Okay, and in problem number 2, they have asked you, question number 1 was show T is linear. That is question number 1. Question number 2, find bases and find bases for NT and RT. Number 3 is compute nullity and rank of T, nullity and rank of T. Number 4, verify dimension theorem. Dimension theorem means the rank nullity theorem. Dimension theorem. Remember, dimension theorem is known also called rank nullity theorem. If I do not say it, suddenly you may become puzzled and you may think that sir has not discussed dimension theorem with us. So you have to know that it is synonymously known as dimension theorem. And finally, number 5 is that verify whether the transformation T is 1-to-1 or onto. Okay, so this question number 2, 3, 4, 5, 6, these questions are actually based upon that. So let me select a question which is the easy question, because I'm going to solve easy questions only, and I'm going to leave the tough ones for you, because I'm very bad in doing mathematics. So I'm always afraid of tough problems. So I'm going to select an easy problem for me. The transformation I'm going to choose is R3 to R2, defined by T of A1, A2, A3, A1 minus A2 to A3. I can remember that in the last class, I also discussed this problem, and where I found range space and RT, NT and RT was found. So let us solve this particular problem once again. In the last class, I didn't show that this particular transformation is whether it is linear or not. In the book, it was claimed to be linear, but we didn't verify it. So let us first of all verify the linearity of the transformation as has been asked in the problem, one after another. So let us start. We know that 0, 0, 0 is the zero vector of R3, and 0, 0 is the zero vector of R2. Now, according to definition, T of 0, 0, 0. I shouldn't write definition. Definitions here, by definition, I actually mean the rule. T of 0, 0, 0 is actually 0 minus 0 into 2 into 0, comma 2 into 0, and which is 0, 0. So what we see that, see, I have not started the problem, but the countdown of the class has already started. So T of the zero vector of R3, T of the zero vector of R3 is giving you the zero vector of R2. Okay, and therefore first criteria is satisfied. This is criteria number 1. Number 2, because if you can recall, there was a theorem like this: T of 0 bar must be equal to 0 bar, 0 bar V must be equal to 0 bar W. Okay. Second is, let us select scalars A and B from the real field, because here R3 and R2 are vector spaces over the field of real numbers. So let us select scalars from A. Okay, let us not select it from, okay, I can select it from R, no problem. So AB from R, okay. And let X comma Y belongs to R3. You know that I'm going to show that whether AX plus BY belongs to R3 or not. This is the question. Sorry. What was the result? Not what was the definition? Definition given in the property number 4 was that, yeah, oh sorry, not this. I mean, this is the property of the subspace. I'm actually going to show, see, sometimes I also become confused. I'm going to show this property. If I can show that T of AX plus BY equal to ATX plus BTY, okay, that property number 4 I'm talking about, then I can say that it is a linear transformation. Okay, so let us do it in the next page. So since X comma Y belonging to R3, therefore X will be of the form A1 A2 A3, and Y will be of the form B1 B2 B3. Then AX plus BY, this will be equal to A into A1 A2 A3 plus B into B1 B2 T of this will be equal to T of B1 B2 B3. Okay, now this is equal to T of A1 plus B1, A2 plus B2, A3 plus B3. By the definition of the transformation, we have A1 plus B1 minus A2 plus B2. I hope you are understanding. And this is, just look at the definition of the transformation. So I can write it as AA1 plus BB1 minus AA2 minus BB2, 2 of 2AA3 plus 2BB3. And this can be written as AA1 minus AA2, 2AA3 plus BB1 minus BB2, 2BB3. Now we can take the scalar common. We will get A1 minus A2 and 2A3, and we can take B common. We'll get and 2b3. And you know that this is T of A1, A2, A3, and that is T of B1, B2, B3. And we can write it as A T of X plus B T of Y. Therefore, T is linear. T is a linear transformation. I hope you have understood the points. So first part of the problem is done. The second part of the problem was what? Let us check. We are going to find the bases of NT and RT. Okay. So before we find the base of NT and RT, then first of all, we have to find out what is NT. Okay. So I'm going to the next page. Part B. By definition, we know that NT is equal to all such vectors of V such that Tx is equal to 0 bar. Now here the vector space V is R3, and we have to find all such points of R3 such that Tx equal to 0 bar. Now since X is a point of R3, we can write it as A1, A2, A3 belonging to R3, and this will be equal to T of A1, A2, A3, 0, 0. Remember, I'm not writing 0, 0, 0 because the image will be in the R2. So that will be equal to all such points of R3 such that A1 minus A2, 2A3 is equal to 0, 0. And all such points of R3 such that A1 minus A2 equal to 0 and 2A3 equal to 0. And from this I can write it as A0, where A belonging to R. Why it is so? Because since A1 equal to A2 and I am treating it as A, I am giving it a name, say A. And also it can be written as A into 1, 1, 0, and where A belonging to R. So this is the null space or kernel of T, and you can write also this as this span of this. So linear combination, NT is the linear combination of this point. But we know from our previous result, one of our previous result, that see, probably I have not proved the result, but I'm going to use it. So the result says that a set containing a vector V, a singleton set of vector V, is always Li, linearly independent. Therefore, this vector 1, 1, 0 is Li. Now this vector and this is Li, and span of this vector is becoming NT from our calculation. Therefore, this vector 1, 1, 0 is a basis of NT. And since only in this basis only one element is there, therefore dimension of NT or nullity T is equal to 1. So this part is also done. What is the next part? Next, we have to find the RT, and we have to also to find the dimension of that. So we are going to do it in the next session because this session is going to end soon. So try to look at this particular problem, what I have done here over here. First of all, I have shown that it is linear transformation, and then I have found the span of T. And here in this part I have used a result. Here also I have used a result. Here also I have used a result. So all these are outcomes of some certain theorems and results. So let us stop here and let's wait for the next session to begin.